if we're going to be moving on to further equations, the natural next place to go would be, well, polynomials. Polynomials are the general descriptor for any equation written in terms of powers of x, where we say the polynomial is in standard form if on one side we have a 0 and on the other we have our terms arranged in descending order of degree, that is power of x, where the largest is said to be the degree of the entire polynomial as a form. And our methods for handling these are actually somewhat similar, as we'll see, to what we did with quadratics and, to an extent, linear things. So for our first example, we want to solve the equation 4x to the fourth equals 12x squared. So when we're dealing with solving these things, the purpose of standard form really is because it makes it easier for us to see the process. If we move that 12x squared over, we would have 4x to the fourth minus 12x squared equals 0. And then from here, we can actually factor this because we see that we've got a 4x squared and a 4x squared there. So we'd have 4x squared times, pulling out that, x squared minus 3 is still equal to 0. And in this case, by the zero product principle, that tells us that either x is equal to 0, or, from there, plus or minus root 3. Because you pull the 3 over, take the square root, you get plus or minus root 3. So if we wanted to write this as a solution set, we would have the values -3, 0, and 3, following a basic factoring scheme. And that one was maybe a little bit too easy, so let's get one that has a little bit more next. So for this, we want to solve the equation x cubed minus x squared equals 4x minus 4. So for this, again, standard form might be illuminative in terms of what's going on. In that case, we would end up getting x cubed minus x squared minus 4x minus 4 is equal to 0. And to solve this, what we're going to do is factor by grouping. I guess that's a slightly different strategy, but we can see that if we pull a 4 from this group, we'd get an x minus 1. If we pull an x squared from that group, we'd also get an x minus 1. So in particular, we'd have an x squared times x minus 1 minus a 4 times x minus 1, where all this would still be equal to 0. It's a matter of recognizing that we have two things we can possibly match up there, where with those grouped, we can then pull those two together across that subtraction to write this as x squared minus 4 times x minus 1 is equal to 0. And hopefully it's pretty clear about what we can do with the zero product principle there to get our answer. This one's one of those nice square roots. That's just a linear term. I'll leave it to you to check to be sure, but, well, we would have that x is equal to plus or minus 2 or 1. So to be specific, if we want to get the solution set here, where again, I am going to leave it to you guys to verify this, but it's pretty straightforward if you want to. We would have -2, 1, and 2 as our potential solutions. Or just for reference, there are versions of things like the quadratic formula for higher degree polynomials. In particular, I am aware of both a cubic and quartic, degree 4, equation, but for reasons that you can probably tell now, they don't really get used that often. Generally, we like to be able to fall back on our nice tricks. And we'll see one more later, but for now, the next thing we're going to look at is, well, a natural place to go because we talked a lot about roots in the context of polynomials. So maybe we should see what happens with roots in their own context. Talking about what are called radical equations next.